Hello, welcome to our talk titled rvnewop, a RISC-V new instruction recommender system. My name is Nagendra, and I'm going to start, walking through a quick outline. We're going to talk a little bit about why we wrote this tool, what's the purpose of developing this tool, and then go into a little bit of detail about how the tool is engineered, what are some current limitations, what are some current requirements it enforces, and finally some results that we have, followed by a quick demonstration of the tool at work so that it gives you kind of a nice insight into what exactly the tool is able to do and how does it kind of produce results. And hopefully we'll have some live Q&A right at the end. Architecture specialization, right? As we all know, we have kind of reached the post-Moore era where we do not get, transistors, density in transistor packing anymore. And this graph on the left, borrowed from Daly's article from Communications with ACM, kind of shows the difference in performance between a traditional CPU and an ASIC. Just focusing on the bars at the left for the deep learning workload. The metric here is images per watt. There is nearly a 15x difference between the traditional CPU implementation versus a hardwired ASIC. And we have all been aware of this. And this is much more relevant now in the post-Moore era as specialization has emerged as the major architectural technique to continue to improve performance as applications continue to require increasing compute throughput and so on. However, specialization by building custom ASICs tends to have some challenges, especially where you're looking at an application space that is diverse and rich and growing and emerging. You don't want to bake very specific constructs into your hardware, and you kind of want to maintain the attraction of a general purpose programmable engine. In this context, we look at our tool essentially as a way to specialize a general purpose ISA. And of course, we're looking at RISC-V as the foundation for exploring such a capability. Domain-specific applications are many. There are examples from different domains, and I have just listed a few of them as just to trigger some ideas. Trigonometric functions in motor control are one class. In ML and neural networks in particular, there's been a lot of specialization opportunities coming up in the form of newer floating point formats such as brain float, 8-bit floating point, and newer quantized data types, some like ternary weights or maybe 12-bit weights and so on, being able to explore sparsity and pruning in neural networks in order to achieve performance. So all of these things tend to bring some newer requirements for data processing. Efficient support for industrial protocols is another. And finally, last but not least, we've had several signal processing acceleration examples like speech, audio, video, where typically lots of different standards have emerged, and some are certainly have been accelerated through specialization techniques. It's in this context that RISC-V provides us with tremendous opportunities. The base ISA, for example, the RV32I, the integer 32-bit baseline, comprises of only 40 instructions, while the standard itself has explored several extensions, many of which have already been ratified and standardized, including compressed, the multiplication, atomic, various kinds of floating point, and of course the vector extension is currently being worked on, as well as several others like bit manipulation, packed SIMD, and several others that are currently undergoing the standardization processes. So the opportunity with RISC-V is that you can kind of pick and choose your, starting with your base ISA, to bring different kinds of extensions to fit the architecture that you implement to suit your application space. And what we kind of want to enable with our tool here is to be able to build your own ISA with RISC-V. This table here is a table obtained from the specification, where I have highlighted about 4 opcode spaces that are earmarked for customizations. These are denoted custom 0, custom 1, custom 2, and custom 3. And these 4 spaces are essentially left open for bringing application-specific or domain-specific instructions to your main ISA, so that you can kind of basically leverage very specific characteristics that you want to implement in your hardware. And there could be other kinds of extensions as well, such as wider instructions. So it is in the context of this specialization opportunities that we look at building our tool. And rvnewop, the name that we've used for our tool, is essentially an architecture exploration and specialization tool. Its job is simple. It looks at a bunch of applications and tries to recommend new instructions. That's pretty much what it does. Here in this demonstration, here in this block diagram, these applications 1 through n are essentially input to this tool. As we will show later, these applications are basically the inputs that the tool consumes are execution traces of these applications obtained through some kind of a tool like a simulator or any other piece of hardware, and that are input to this tool. And this tool understands the base ISA plus a whole bunch of extensions, and it tries to effectively analyze patterns of execution that it finds in these input programs and comes up with customized new instructions. That's pretty much what the tool is going to do. The current capabilities of rvnewop, essentially, it accelerates the task of finding as well as encoding specializations. It not only finds patterns of compute that could be collapsed to form new instructions, but it also goes ahead and encodes these new instructions in one of the custom opcode spaces that we looked at a couple of minutes ago. It also, as a byproduct, it reports on usage of standard extensions, registers used, instructions used or not used, and other attributes. So it kind of gives you a feel for whether the extensions are proving to be useful for the kind of code that you're looking at or not. So it's just some quick feedback on the side. The tool also automatically adds new encodings to the golden reference spike simulator. This is kind of just to enable being able to implement the newly found instructions back into a simulator so that you can kind of take advantage of it and iterate through the process of exploring additional things. And at present, the tool models the IMACV standards over the RV32 baseline. And we plan to cover all the other standard extensions as well as extend the support to RV64 shortly. That's kind of where the tool is currently at. As I mentioned before, this is a tool that is essentially open source. It's Python 3.x based. Here is a link to our GitHub repo. You're welcome to clone this repo and download and look at the code. We have attempted to organize rvnewop as a collection of Python modules that are assembled together to provide the end capability of finding new instructions. Various modules are provisioned for instruction parsing, RV32 extension specific decoding, to identify basic blocks of execution from input traces, to do data flow analysis, and of course other things like input trace reading, output encodings, and those kinds of mechanisms that we need to put together around the whole framework. The point is that newer analysis and output capabilities can hopefully be more easily added since it's open source and it's implemented in the popular Python programming language. This picture here is not meant to be too detail oriented, but just to give you an idea of how our tool is kind of put together using various building blocks in Python, starting with an RV format parser. As we consume input traces that contain PC values and the instruction words corresponding to the instructions at those PC values, we need a capability to parse these instruction words to extract what kind of instruction it is. Essentially, we have to decode the instruction from the instruction words, and that's where the format parser comes in. And there are various extensions that the tool automatically supports, with more to be added. And finally, it constructs an internal representation of each instruction that is then assembled into the program. And on top of this, we do compiler-like analysis to extract basic blocks, to understand control flow, and also to do data flow so that we can identify sequences of instructions that could be safely, functionally correctly reduced to form new complex instructions. And of those, essentially the tool filters things that are not that interesting and identifies only the top few candidates. These things are, of course, configurable. Given that it is Python, you can control how many new instructions you want to consider and so on. And finally, the tool outputs new encodings. This here is a little bit more detail into the working steps that the tool uses in finding new instructions. Starting from the left, we'll briefly talk about each of these steps. The first thing it does is, starting with an input trace of execution of an application program, it identifies basic blocks, right? Basic blocks is standard compiler stuff. It's finding sequential pieces of execution. It then splits each basic block into what we call as subblocks. And a subblock in our definition is essentially found out by looking at a basic block and delineating different sets of instructions that are separated by memory accesses. So if you have a memory access and a memory access, and there are compute instructions between two memory accesses, this set of compute instructions in between constitutes a subblock in our definition. And then once we do that, we link all of these subblocks as per the control flow. Since our execution trace contains the branches and so on, we are able to link all the subgraphs into a program level control flow graph. And then we are ready to find candidate graphs. Here we have highlighted 4 candidate graphs, G1 through G4, that the tool has found. Essentially, the candidate graphs that the tool finds have to satisfy certain requirements for them to be collapsible to form new instructions. We have a little more detail in the next slide that talks about this. Once we have found out candidates, the tool tries to see if different candidates happen to be identical. It's often possible that across different pieces of code that's being executed, the same instruction pattern might have been found out across different programs or across different functions within the same program. And therefore, the tool tries to do some kind of isomorphism check across all the candidates so that it generates only one new instruction if it finds multiple copies of the same subgraph that it should reduce to form a new instruction. So in this cartoon, G1 and G4 were discovered to be isomorphic, and therefore it basically collapses them into a single new candidate instruction that it has to recommend. Then it proceeds to estimate the potential savings, and this it obtains using some kind of a histogram of the input trace, where if the input trace provides some guidance as to which functions or which programs are executed more often, or the sizes of the loops and so on, based on that data that it finds in the execution trace, it's able to estimate the impact of achieving this reduction. And therefore, it kind of does that and estimates potentially the cycles saved. And using the data, it restricts its attention to the top 5 or 10 most useful new instruction candidates that it finds. And finally, it performs the actual instruction encoding for those top candidates that it finds. That's pretty much the overview of the tool. I would like to talk a little bit more about finding candidates. The tool looks for candidates that satisfy 4 properties, 2 register sources to the candidate graph, because they're interested in finding new RISC-like instructions that satisfy the property of 2 register sources and 1 register destination. That's why it limits its attention to graphs where only 2 registers are inputs, and the graph has got a single register destination. And with the additional requirement that no intermediate registers should be live outside the subgraph. And this is essential to make sure that when we replace the entire set of individual instructions by a single new instruction, we would not have violated any functional correctness of the original piece of code. So that's kind of why we impose this restriction. And last but not the least, we want to make sure that only 32-bit encoding is done. And that means we have to also ensure that all the immediate constants that the graph requires can be accommodated as well. So that is an additional check that is done by the tool. Here are some out-of-the-box results on MBench and CodeMark benchmarks. We didn't really look at the code or optimize or modify any of these source codes. We didn't do anything special with our tool. But this is just an out-of-the-box execution of the tool across all of these benchmarks. And you can see that on some of these workloads like MatMalt and CRC, the tool finds significant opportunities. We went ahead and looked at the savings obtained by just the top 5 most useful instructions. Clearly, because that's practical, we do not want the tool to recommend hundreds of new instructions. That wouldn't be practical. And we did look at the savings projected by just the top 5 candidates. And it turns out that in the majority of the workloads in these benchmark suites, it is indeed the case that most of the savings, over 90% of the savings, come from just the top 5. And in MatMult, for example, all the 100% of the savings come from just the one instruction. We also try to make sure that the new instructions are not complex. By complex, we mean that the depth of the graph is not too deep, which might mean that the new instruction may not be realizable without breaking it into different pipe stages, which we kind of wanted to avoid. And therefore, we looked at the depth of the graph, and we find that most new instructions fit within a depth of 4. And we also went ahead and implemented these new instructions over an open source RISC-V design and verified that it didn't affect our timing in the critical path. So our clock frequencies did not have to slow down to incorporate these new instructions as single cycle instructions. So that gives us some confidence that we are looking at it the right way. With that quick overview, I will switch to a pre-recorded demo that was done by one of our students, Pranay, so that we can kind of give you a little bit more insight. And this is a very simple demo, takes a look at a very simple piece of C code and walks through the whole steps of getting a histogram, running it through the tool, and finding what the tool finally reports. So that way you guys have a more clear picture for what it is going to do. Here it is.
Hello, my name is Pranay, and today I will be demonstrating the rvnewop tool with an example. So let's look at the C code as an example. The main bit of computation that's occurring over and over again is on line 9, where we're doing 2 left shifts and then an addition of those 2 values, and we're storing that into this variable here. We want to focus on this bit specifically throughout this whole example. So we're able to compile this using the RV32IC, which is the 32-bit integer baseline along with the compression extension. And let's take a look at the object dump that's generated from that. So let's look specifically at the compute function. And here we can see this is what that instruction is turned into. It's turned into these 3 assembly instructions. These 2 left shifts, one of them storing the value into A5, one of them storing it into A4, and we're adding A5 and A4 together and storing it back into A5. As discussed earlier, we aren't considering the memory loads and stores, but only the compute instructions. So now we're able to compile and run this code through Spike and collect a histogram of the execution of the program. For illustration, we have one of those histograms here, and let's just take a look. The format of the histogram is we have the PC value here, and this is in hexadecimal. Then we have the instruction encoded in hexadecimal as well, and then a count. This is just how many times this instruction has run. So looking at the bottom of the file, some instructions, of course, have run more than others. So now we're able to run our sample tool topinstruction.py with the histogram file as our input. So let's just run it here. So this tool builds on the analysis carried out by the rvnewop core modules, such as analysis.py, subgraph.py, and so on. And our tool is able to determine new candidate instructions and finally report the top 10 most useful new instructions. Although in this example, we're only looking at 1 new instruction. So looking at this output here, we can see that it gives us the number of cycles saved with our new instruction, along with the depth and various other information. We're also able to show a visualization of that new instruction. So our program is able to create a PNG of the new instruction. So we've got these instruction nodes where we have the 2 shifts and the addition, and we're also showing the 2 register nodes as well as the 2 immediate constants. So these edges essentially are showing the way the data flows. And so the data is moving from bottom to top and eventually ending up at this add instruction here. Top instruction.py finally will encode this new instruction in either the custom 0 or custom 1 space. And this will use the same overall instruction structure in terms of where the register sources, destination, and func3 fields are located. The func7 opcode field is not being used in our encoding scheme, and instead we're using those 7 bits to encode smaller immediate constants. Note that our tool also automatically assigns a new name to the new instruction based on the composition of the underlying graph of our instruction. Our new instructions are also output as a JSON file. So let's take a look at the JSON file that's outputted. So here we can see the auto-generated new instruction name. We also store the fields like the opcode, the func3, the source registers, and so on. And we're also able to store the semantic in this graph, and we store it in this adjacency list format. The JSON file serves as a handoff from rvnewop to other tools that can automate updates to design files, compilers, assemblers, and simulators. In our prototype, we update the golden reference spike simulator automatically using contents of the JSON file. This includes automatically updating the encoding.h, the make file, along with automatically generating the instruction execution semantic headers. So let's take a look at those files. So we have this autogen section, and we're automatically generating the match and mask values for our new instruction. And we're also able to create this instruction semantic where we're creating the C code to run this new instruction. So, final notes, rvnewop is under active development. We have currently implemented updating the spike simulator, and in the future, we expect to add support for automatically updating the GNU assembler. Thank you.
Okay, that's hopefully gave you a good idea what the tool is currently able to do. It's an open source Python tool, as I mentioned before, and it's an ongoing project, and we expect to do several more enhancements, including bringing 64-bit support, as well as being able to extend the analysis to do whole program, across different functions to find out even more sophisticated new instructions in the future. Acknowledgements. This work was done with the help of several contributors, Pranoy, myself, Tanvi, Robert Moore, and Professor Krishna Kavi. And the work is funded by the Semiconductor Research Consortium, task number 2943.001. Thank you.